one over there. But regardless of how I cut this, even if this was like 20 by 30, or I would say 100, but 200 feet, it would be separated the same. As soon as you connect to 12 volt DC, it's going to be separated. The charges are going to be separated regardless of the size. This is another experiment. So this is a sheet of aluminum. I made exactly a square, 8 by 8 inches, but this one is a coil, or I would say solenoid, and this 80 turns, and then when I connect this 12 volt DC, even though this is one sheet of aluminum, it is going to act exactly like that, 80 winding or 80 layers of wire. I'll show you. See, when I connect this to 12 volt DC, you can see the top part is going to be south and the arm part is going to be north. See, if I bring over here, it'll be different. And inside is going to be exactly opposite. Now I have south on this side and the north on the bottom, and inside this is going to be north and the bottom is going to be south. And if I connect this to 12 volt DC, exactly the same thing will happen. And it doesn't matter how many turns of wire I have. Like this solenoid, I have 240 turns, and you can see it's like a cylinder is going to be exactly the same. And then this one is like a ball. And this one is like a ball. And it doesn't matter how many turns I have or how big this ball is, it's always the separation of the charges is going to be north and south. And you can even tell, like Earth, we have also, if I take it like this and this is facing me, one side is going to be south and north, and this side is going to be west and east. In fact, the separation of charges is used in automotive industry, and this is an alternator, and what it does, it creates AC or alternating current, and then is converted to DC so it can recharge the battery. But you can tell the separation of the charges is used exactly the same way, and this is a very strong coil, and it has a core like this. When it's excited by 12 volt DC, you can tell this sharp tips, each one becomes like north and the opposite south, and the opposite part becomes south. But the most important thing is, by doing this, they can concentrate the charges on those tips, and when it's rotating in a stator, which is also, it has a lot of ferromagnetic and the copper wires, the electromagnetic induction is the best. And imagine what would happen if these sharp tips were not here, just regular, like a hollow or something like a straight, it wouldn't be any induction whatsoever. This is another experiment, and this is 4 inches, in fact it's 5 kilograms lead, and it's solid, but this one is aluminum, it's 8 inches. What I did, this is like a regular plastic ball, but I covered with 6 layers of aluminum, and exactly like Earth, when I connect this to 12 volt DC, even if the current is applied from the center or from the surface, it doesn't make any difference. So the separation of the charges are the same. So you can see here, when I connect this to 12 volt DC, see what happened? See? Charges are separated south and north, and you can also see on both sides it's exactly like Earth. When I have south on this side and north on the other side, one side is east and the other side is west. So I just wanted to prove that some something in this small compared to Earth is exactly the same. When the charges are traveling inside the solid like this, like a lead, or the hollow like this, they're exactly the same. Charges will separate to north and south. Hi. This is my second part of my theory of separation of the charges, which is the flow of electrons in a wire. The first probably microsecond when the charged particles are flowing in the wire, the charges are separated, and due to this separation, the electrons are going through the Henry-Lorentz forces, which is the deflection, and then consequently they are going through the cyclotron motion. I have some posters here. I show you exactly what I mean. As I mentioned, as soon as the charged particles going through the wire, not only they have the linear motion, but also they have the angular motion or angular momentum. The reason why the electrons are deflected from both sides, or technically is the Henry-Lorentz forces. So when they go through the wire, no matter what the charges are separated, so they are deflected by Lorentz forces. And not only they have kinetic energy, which is the linear kinetic energy, which is half mass velocity squared, they also have the momentum, or the kinetic energy of the angular momentum, which is k half I, which is the moment of inertia, omega squared. And the Henry-Lorentz forces technically is charge times velocity times magnetic field times sine of the angle. But overall, the entire concept is electric field times the magnetic field. So it's the interaction of the charged particles or moving charged particles in magnetic field. This is a drawing of the cathode ray tube. Well, I had to enlarge it, but you can see here, this is the cathode, and the electrons are emitted from the cathode, and they have to go through this neck all the way to the surface. But something important happened here. The electrons are deflected. You can see those electrostatic lenses, also the deflection coils. It's also the Henry-Lorentz forces. So when they go through this tunnel or go through this neck, they are deflected and they are going through the cyclotron motion. And I compared my wire to exactly like a cathode ray tube, but of course this is huge compared to my wire, but the basic or the concepts are the same. I also compared my wire. The charges, when are going through the magnetic field, which is the separation of the charges, is exactly like a magnetron, which is used in microwave oven. Well, of course, this one has 8 poles, but the concept is the same. The electrons are deflected from these sides or from this charged particle, and they're going through the cyclotron motion. And this is done in a science lab. Well, of course, you can see here are the huge magnets on each side, which is a little bit dark. But this is like a cathode ray tube, and the beam of electrons, you can see this is like a light bulb, is deflected because of this magnetic field, which is also the Henry-Lorentz forces. And this one is a little bit more magnified, but you can see this is a huge bulb, and you can see the electrons are going through the cyclotron motion. Well, of course, this part I have to explain. We owe it to great Danish physicist Niels Bohr, and he postulated that when the electrons are dropping to the lower level of energy, they emit photons, and then this is exactly what happened. So you can see that purple color here is the Niels Bohr idea. This was a breakthrough in science, and it's called a scanning tunneling microscope, which was invented in 1981 by two scientists, Georg Benning and Heinrich Rohr. is amazing about this. Before this, we had no idea how big the atoms or molecular level was, but this was a great discovery. And imagine, this is a picture, well, of course it's enlarged, with a scanning tunneling microscope, 7 nanometer by 7 nanometer of a single zigzag chain of cesium atom. And in fact, they also discovered that in a wire of 1 millimeter by 1 millimeter, there are billions of dipoles. And each one is separated by the charges. And without this invention, there was no way we could see through this. This is the conclusion for the theory of separation of the charges. So this is the Earth, and this is 1 millimeter wire, and as I explained before, like 1 by 1 millimeter, there are billions of dipoles, and are separated by charges. But I drew this so you can see when there is no electric field, everything is like dipoles in any diamagnetic or paramagnetic. They are oriented in a random fashion. So in other words, you can see north, south, north, south. They are not in order like this. So when the electric field is applied, well, in other words, the external electric field is applied, you can see the angular acceleration, but in other words, they torque north toward the south, south toward the north, and this is the bottom line. You can see is exactly one part is south and the bottom part is north. But something amazing happened here. If there is no electric field like aluminum or copper, always these dipoles must be in random fashion. They are not straight. But what happened when the electric field comes in, everything is in the same thing. That's why we have north and south. But something amazing happened here. In between here, like this one, and this one, and this one, there's a cancellation. So in other words, they just add up together, but there is no way. They have to push one side of the dipole all the way to the end, and then they enhance it after that. This is another way. One side is north and one side is south. Even in a magnet, permanent magnet, same thing happens. It's always, you can tell, in between is a very weak interaction. When it comes to the poles, in two sides, is very strong. This is the Earth, but as I showed before, in a round is different, in a square is different. When it's round like that, well, of course, Earth is not round. You can see on the equators, like here, is 43 kilometers bulging, but it doesn't matter. Overall, Earth is like a, oblate, or is like a globe. But you can see here, because there is no sharp objects, the way I explained before, the charges are not getting separated. But here you can see the north and north are facing each other. Here the south and south are facing each other. And the other ones here in between are cancellation. It's always the charges are to the subsurface because that's as far as they can go. Well, of course, my analogy to this was like a tectonic plate. And imagine two tectonic plates, one here and one over there. When they push themselves to the boundaries, what happened? We have a bulge over here. So charges are the same. So in other words, these dipoles are the same. They can push each other as far as the surface, and that's as far as they can travel. Like this one is a very strong magnet. But you can see there is no interaction in between, but on the poles we have a lot. Well, of course, there is no current like this one is flowing, but this is like a closed circuit, but it doesn't matter. The concept is the same. You can see, if I divide this again, it's going to be exactly two magnets. If I divide this more and more and more, it's going to be the same. This is extremely strong block magnet, and it can hold up to 100 pounds. But if I can divide this to trillions of small pieces, or I would say up to the molecule level, which is almost impossible, but by scanning tunneling microscope, maybe I will be able to see the smallest particles again again we have north and south. You can see, but when you see here, see how strong they are? This is exactly the same concept. So even in a magnet like this, we should wonder why the charges are always separated. We have cancellation in between the poles, and then if I break this, again, the same thing happens. We will have the cancellation between two poles. If I break this to 4 pieces, 16 pieces, 32 or 64 pieces, it's going to be the same all the way to the molecular level. They will have the dipoles.